I'd like to welcome everyone. Thanks for joining us today on this webinar focused on PFAS remediation. My name is Martin Drager. I'm with Water Services and Technologies here in Canada. And with me is Dr. Grant Carey. So Grant is the president of Pour Water Solutions and has more than 30 years of experience focusing on site characterization and remediation of hundreds of impacted sites. Grant specializes in PFAS, fate and remediation, environmental forensics, groundwater modeling, and visualization. And he's also involved with a number of CERDIP and ESTCP projects with focus on PFAS, in-situ remediation, modeling, and visualization. Grant's also an adjunct research professor at Carleton University in Ottawa and adjunct professor at the University of Toronto. So thank you for joining us today, Grant. I'm sure there's a lot of people interested to learn more about PFAS. So let's quick move on to the agenda. So I just wanted to first start off by reminding everyone this is the second webinar in a series of 4 that we're offering. The first one we already had, and if you haven't had the chance to take a look at it, it is on our website. It's on our YouTube channel. You can take a look at some very good, insightful information about PFAS characterization. And today's focus, obviously, on remediation. But we have 2 more PFAS webinars. One is improved forensics assessments, and the other is evaluation of vadostone sources. So please go ahead at the end of this event and check out our website, and you can pre-register for those as well if you're interested. So in terms of the agenda, we'll go through a quick overview of our company, Water Services and Technologies, and why we're working with Grant on PFAS. Then Grant will take the mic and lead the bulk majority of the webinar, focusing on remediation overview. He's going to look at adsorption, isotherms, so on and so forth. And then we'll break into a question period at the end. Now, that said, if you have a question, we encourage you at the moment you think about it to put that into the chat. We will address all the questions at the end of the webinar. If we don't get a chance to address it, we'll send you an email and hopefully address it in that capacity. You will also see a couple of polls pop up on your screen. If you would be so kind to just contribute to that, it'll help us improve the webinar content and help us learn a little bit more about your needs with respect to PFAS. So let's move on to a quick overview of Water Services and Technologies. So our company was founded in 2017 in Brazil. We now have 2 offices in Brazil, and our core services is really environmental services and technologies for water resources management. We dominantly are helping mines, but we do support private sector industry and public sector with their water resources challenges. The founder, Dr. Nielsen Giger, some may be aware of him. He started a company back in the 90s called Waterloo Hydrogeologic. It was a software-focused company. Some of the products that are still in use and globally recognized, visual mod flow, for those of you who are familiar with numerical modeling, and also FlowPath 2, which was a standard for capture zone delineation in the UK for years, among other software, and also environmental data management. He inspired and was the visionary behind HydroGeoanalyst. So we are, as a company, very technology driven. It's in our blood to use, adapt, and develop technology. And one of the technologies that we're seeing a subtle increase in demand right now in Brazil is technology that can support PFAS site investigations. We're seeing that in Europe, dramatic increase in demand for learning and understanding PFAS, and also in North America. So we have an interest in working with Pour Water Solutions, Grant's company, and using the software Visual PFAS for some of the projects that will be coming online in Brazil in the coming months and years. We've also worked with Grant in the past at Waterloo Hydrogeologic, where he developed some software for monitored natural attenuation and biodegradation. So Grant is quite a techie as well and very knowledgeable in remediation. So we also offer technology. Visual PFAS, you'll learn a little bit about, is something that we've been asked by Grant to help sell globally. If you're interested, let us know. And also we offer training globally. We've trained thousands of professionals around the world on modeling, aqueous geochemistry. So that's our interest, is we think alike, and we also we have a need for his software. So without further ado, I think we can go ahead, Grant, with your part of the presentation. I think everyone's excited to learn more about how you approach remediation with respect to PFAS, and certainly I am as well. So the mic's yours.
Excellent. Thanks, Martin. And hello, everyone. Thanks very much for attending today. I really appreciate your time. And I wanted to thank Martin and the rest of the team at Water Services and Technologies for hosting this webinar. They really know how to host a professional webinar series, so much appreciated as well. And before I forget, because I know I will, I wanted to mention, so there's a lot of slides in the deck today. Anybody who'd like a copy of the full presentation, just send me an email, gcarey@poorwater.com. And any of the papers I'm referencing today, if you'd like copies of those, just request those by email as well. I'm happy to forward those. So as Martin mentioned, I've been really fortunate to actually be part of 7 CERDIP and ESTCP PFAS projects right now for the U.S. Department of Defense. And that's one of the big things that I'm here today in terms of goals, is I want to share with you the lessons we've learned through the use of colloidal activated carbon as an in-situ remediation technology for PFAS. And on top of that, I wanted to share with you the visualization methods we've actually been using to look at both pre-remediation and post-remediation data at these PFAS sites. Because as a lot of you know, actually evaluating all these PFAS data we're collecting is not an easy thing. So we're looking at a couple different ways of visualizing the data. So that'll be part of this presentation as well. And in terms of the CERDIP and ESTCP projects, my main role in these projects is actually modeling. I model both the PFAS transport both within the barriers and downgrading the barriers as well. We're really interested in trying to better understand how long does it take to flush out a PFAS plume, downgrading of an adsorption barrier, or even a pump and treat system. We're going to see the same sort of desorption effects. And the model I use is called the in-situ remediation model, or ISR model. That's a proprietary model developed here at Poor Water Solutions. Initially started back in the late 90s as a biodegradation model, electron acceptors, electron donors. Since actually more like 2015, we've been updating that model, especially for PFAS adsorption barriers. And most recently, so some of the things I'm working on with some of the research projects I'm involved with now, we're looking at competitive adsorption effects in the barrier. How does that affect longevity of these barriers? The effects of aging of the activated carbon in the barriers, colloid transport, so CAC injections. What's it look like during and after the injection? And branch decay chain, so we can better evaluate precursor transformation to some of the potentially regulated PFAS compounds. So a lot of you are probably familiar with colloidal activated carbon. If you haven't heard of that term, you've probably heard of PlumeStop, which is a Regenesis product. And this colloidal activated carbon, these are really tiny activated carbon particles. And because they're so small, they're easy to inject into sand aquifers. So the way it works is when these barriers are constructed, there's a liquid solution that contains these colloidal activated carbon or CAC particles. Temporary wells are used to actually inject the liquid solution into the barrier footprint. And after injection, these activated carbon particles will move a short distance away from the injection wells, where they eventually attach to sand grains within the barrier. And the image on the right shows an example of these small little carbon particles when they've actually been attached to a larger sand grain. So when we're designing these barriers, the typical target concentration after injection is 2,000 milligram of CAC per kilogram of soil. So that's the target that we're trying to shoot for. And that corresponds to what we call a fraction of CAC, or FCAC, of 0.2%. So it's kind of the same thing like FOC. We just call it FCAC because now it's colloidal activated carbon as the fraction we're interested in. And that is, if you're thinking about longevity, how long do these barriers last? That's probably one of the biggest driving factors, is how high does the FCAC get within the barrier after injection? the higher the FCAC, so the higher the amount of activated carbon in the barrier, the longer it's going to last before we may see breakthrough. So we know that PFAS absorb really strongly to activated carbon. So when we construct these barriers, we've got a PFAS plume coming in from the left, high concentrations comes into the barrier. The PFAS actually absorb really quickly to that CAC in the barrier, and the groundwater coming out the other end has been filtered. So over time, as we have continued long-term PFAS mass flux into that barrier, eventually the PFAS plume moves through the barrier and will break through the end eventually if there's an ongoing mass flux over a long time. So the big question is, what's the longevity of these kind of barriers? So let's actually look at a result. This is results from a monitoring well installed inside a barrier, a PlumeStop barrier at a Navy site. So now we're looking at a radial diagram that has sulfonates for the axes. And if you start at the left, that's PFBS. That's the shortest chain sulfonate in the diagram. And if we go radially clockwise around that diagram, we see the chain length increasing up to PFAS at the bottom. And in terms of data series, there's two data series on the diagram. The red series are the pre-remediation concentrations of all these sulfonates. And the smaller green series, those are the post-injection concentrations measured at the monitoring well in the barrier 3 months after injection. And you can see everything's declined by orders of magnitude. PFAS has gone down 3.5 orders of magnitude, for example, just looking at the concentration before remediation and then after. Almost all of them have non-detect symbols, meaning that most of these sulfonates were not detected. Only a really low detection of PFBS at about 1 part per trillion, 1 nanogram per liter. So that shows really effective remediation after the barrier was installed. And then looking at carboxylates on the bottom radial diagram, we actually see something pretty similar. We've got the long chains like PFOA, that's typically regulated, also declined by about 3.5 orders of magnitude. Same with PFHXA, PFHPA, they decline a couple orders of magnitude. The two short chain carboxylates are a bit different though. PFBA and PFPEA, they haven't absorbed as well to the activated carbon. And that's actually expected because those two compounds, the two short chain carboxylates, are known not to absorb very well, whether it's activated carbon, a lot of ion exchange resins. They're the toughest ones to absorb. So, but that's okay because those compounds typically aren't regulated. It's typically the long chains like PFAS, PFOA that are regulated. So as long as we're getting those long chains not breaking through for a fairly long time, we're good. So getting back to site characterization, when we're looking at characterizing PFAS sites, there's a lot of different things we need to look at. Where do we have exceedances of all the compounds that are actually regulated? We might be looking at short versus long chain and down through the list. Is degradation occurring? Are we getting attenuation of PFAS along a flow path, which can happen if we're getting forward diffusion into silts and clays? So there's a lot of things here. And you see number 7, that's the one we're going to talk about today, remediation monitoring. So in all of these things, we're actually not looking at one species of PFAS at a time. We're actually looking at how some PFAS change with respect to other PFAS, which are higher, which are lower, how do they change along the flow path. So when we're looking at interrelationships like this, when we're looking at short chain versus long chain, precursors versus their daughter products, we actually have to look at a lot of PFAS compounds at the same time on the same map. So a couple ways we've been doing that more recently is using radial diagram maps and stack bar maps. And everybody's looked at stack bar maps in Excel, but it's typically been harder to plot them on a map. But we find actually putting them on a map and being able to look at spatial relationships, trends along a flow path, that really adds a whole different dimension to what we can learn from these different tools. So one thing that's actually been pretty common is pie charts. So stack bars on a map, that's really looking at the proportion of different chemicals relative to the total of the chemicals. And pie charts are actually the same thing. One thing I find is that the stack bar maps I find a little bit more intuitive. Because in this example on the left, we're looking at the shortest chain on the bottom of the bar. And as you go up the bar linearly, we're going from shortest chain to longest chain. So it's a little more intuitive than the pie charts, where I always have a bit of trouble visualizing where does the short chain start, where does the long chain end. The other thing we're doing with with stack bar maps is we're actually putting the tick marks on the bars actually on the map, which makes it a lot easier to visually estimate the proportion of each of those chemical intervals, whether it's 5%, 10%, 25%. You can tell that pretty quickly with the tick marks in place on the bars, whereas the pie charts, it's a little bit harder to visualize that once you get below, say, 25% of a proportion. So, as Martin mentioned, there is this visual PFAS software, which we released a few months ago. That right now is really focused on radial diagram maps and stack bar maps. So, taking all these PFAS data and allowing us to add these things to the different site maps. We're also building in over the summer heat maps. So, whether it's looking at heat maps on a site-based map, or even looking at a well and looking at all the PFAS chemicals coming out of, say, method 1633, we can use heat maps on a well by well basis to see what's high and what's low through all the different wells at a site. So there's a lot of things that we're building in. I'm not going to make this a commercial webinar. It's really more about the remediation options. But just wanted to mention this. If you want more information, you can go to www.visualpfas.com, and there's contacts there and a lot of case study information if you're interested. And you can also look at the user's guide with more information on how the software works. So something else you may be interested in, we actually had a journal paper just released this week at the Remediation Journal. It's available online. We've got a link at the visualpfas.com website. The cover of the journal actually has a slightly different case study than what's described in the paper itself. We talked about both in the cover, we're talking about how we can use radial diagrams and stack bars to visually fingerprint different source contributions to groundwater, pore water, and surface water at a Michigan Air Force Base. And the paper itself in the journal, that talks about a South Dakota Air Force Base where we've got a number of different examples of how we can use radial diagrams and stack bars. And what we're seeing on this slide is how we can use either one of those methods to look at top assays and how we evaluate all that data that comes out of the top assay. So today, I'm actually going to focus on remediation. So first, we're going to talk about adsorption isotherms, because that's the second thing that really drives the longevity and the success of an adsorption barrier. How well do the different PFAS absorb to the activated carbon we're injecting? Well, we'll spend probably most of our time today looking at a detailed case study. It's a Navy 2-year pilot test where PlumeStop was injected. And then we'll finish up pretty quickly near the end looking at modeling results, actually, for a South Dakota Air Force Base, where we were looking at what's the best place to put an adsorption barrier. Is it at the source area, at a down gradient boundary of a site, maybe a couple PRBs at the site? So we're looking at what's the best approach or best strategy to use. And at the end, I'll kind of give you some of my thoughts, my personal thoughts and recommendations if you're considering an adsorption barrier. What are the things you need to make sure you're looking at before you decide on what to put in, and how to design these to make sure they last a long time. So I'm sure a lot of you are aware, the two classes that we talk about quite a bit of PFAS of interest. There's the sulfonates on the left. There's the carboxylates on the right. PFOA is the carboxylate. And I've highlighted the ones in yellow. Those are the long chain. And the thing about long chain PFAS is they adsorb pretty strongly, especially PFAS. And that makes them bioaccumulate more in our bodies, which makes them more toxic. And that's why in a lot of jurisdictions, whether it's federal or provincial state, we typically see regulations for the long chain compounds because they bioaccumulate the most. They tend to have higher toxicity. The ones that aren't highlighted, those are the short chain PFAS. And they typically don't adsorb as well as the long chains, which means they don't bioaccumulate as much in our bodies, which means they're typically not as toxic. And that's why you actually, a lot of jurisdictions don't see regulations for the short chain PFAS. And that's important because if you're looking at an adsorption barrier, you want to know what the relative concentrations are, say, of short chain versus long chain coming into that barrier. And in terms of regulations, this is something I've showed in a few presentations. I thought it might be helpful, where the long chain compounds, where we right now have federal MCLs in the US, they're really low MCLs, obviously, 4 to 10 nanogram per liter. But the short chains like PFBS, PFBA, in terms of residential screening levels, because they don't have MCLs, there are federal residential screening levels, RSLs in the US, for short chains, but they're much, much higher, 4 to 5 orders of magnitude higher. And that's probably because they tend not to bioaccumulate as much. They're not as toxic. So that's a big thing in terms of remediation, is evaluating what are the actual regulated compounds. If something's not regulated, it's not as toxic. It's okay if it doesn't absorb as well. We're really focusing these remedies on the regulated compounds. So for an adsorption isotherm, that really tells us how strongly different PFAS absorb to activated carbon that we're injecting into the subsurface in the footprint of these barriers. So isotherms are actually pretty simple. It's got an x-axis, these charts, aqueous concentration on the x-axis, that's like a groundwater concentration, and the adsorbed concentration on the y-axis, how much is absorbed to the activated carbon. And we've got one line here. This is a Freundlich isotherm, which plots as a straight line when you've got the x and y axes on a log-log scale. And what we're looking at is an isotherm for what I call a single species solution. So it's basically water and PFAS mixed with activated carbon. And that's it. There's nothing else in that solution that competes with PFAS for adsorption sites in the carbon. So we get a really effective adsorption in that case. So now when we take a groundwater sample that has PFAS, but it's also got a lot of other PFAS constituents. It's got precursors, which absorb pretty well to carbon. It's got high organic carbon in this particular sample that we analyzed, about 24 milligram per liter. So there's a lot of things that compete with PFAS for adsorption sites on the carbon. And we can see the adsorbed concentration with the groundwater sample is close to 10 times smaller than the adsorbed concentration when only PFAS is actually in the water. So that shows you can have competition, and that really affects the adsorption strength, even of PFAS, which absorbs really strongly to activated carbon. So now looking at other compounds from the groundwater sample, this is a sample collected at a site where PFAS were actually fairly high in concentration, collected in a plume. We can see 6,2-FTS, that also absorbs pretty strongly. Not as much as PFAS, but it's still pretty high. And then below that, in terms of absorption strength, we have PFHXS and PFOA. And those compounds are all pretty typically detected at AFFF impacted sites. So one thing to keep in mind is if you have a site, say, with high concentrations of some chemicals, DRO, for example, is something we typically see at AFFF source areas. If it's high enough in concentration, it can adversely compete with the regulated PFAS and reduce the longevity of a barrier. Another thing to look at is natural organic matter, which we might measure through DOC or TOC. If that's really high, that might also compete and reduce the longevity of a barrier. So it's important you look at all these competing factors. And some sites you might even want to actually develop a site-specific isotherm, depending on your site chemistry and how complex it is. So let's look now at a Navy site where they did a 2-year pilot test. And what we found at this site is the actual fraction of CAC in soil, it actually varied quite a bit vertically in the barrier. So looking at a simple chart here, the x-axis is that FCAC. That should actually, that's not milligram per kilogram. That is basically percent. So 0.3%, 0.2% is our target. It shouldn't be milligram per kilogram on the axis there on the x-axis. And we can see this is actually plotted with height above the wells. These are shallow wells we're going to look at for this particular site. And you can see near the bottom of the well screen, we had really high CAC. But there are other parts of the well screen, like here, where CAC was quite low. And then as you move up the well screen, CAC was higher near the middle of the well screen. And then CAC declined in concentration in the soil as we continued to go up vertically to the top of the well screen. So when we actually modeled that, we created a 2-dimensional reactive transport model. So it's a cross-section model where we actually built in that CAC profile and how it varied with depth with the well screen. These are shallow well screens we're looking at, 5 feet high. And we actually, when you look at how CAC is low or close to zero near the top of the well screen, you can see this is a model of PFBS moving through a barrier. The barrier is the thick line. And we see near the top of the well screen, PFBS is actually broken through because there's really no CAC in that really thin top interval. But everywhere else in the well screen is at or below PFBS detection limits. So what happens is when you have these really thin intervals with little to no CAC in the well screen, you're going to see a small concentration that might be detectable, but is pretty stable in time until the next low breaks through down here. So that's something to keep an eye on as you want to measure after these barriers are constructed. You actually want to take a look at, well, what is the CAC concentration with depth and with distance through the flow path in that barrier, because that can certainly impact the longevity of these barriers. So for this study, I wanted to acknowledge the Aptum team led by Dr. Paul Hatzinger. They did a great job looking at high-resolution monitoring of this 2-year study. Really helped us understand what's happening before, during, and after the PRB construction. Dr. Tony Danko from NAFAC XWIC and Dr. Brent Sleep from University of Toronto were also part of this team. So before the PRB construction, so you can see the PRB was eventually put in over here. It's about 12 feet in, we call that the width, parallel to groundwater flow. The length is about 30 feet, perpendicular to groundwater flow. Before that was actually put in, we had 3 borings that were installed, and groundwater grab samples were collected at different depths of those 3 borings. And you can see we collected samples at 5 discrete depths, including samples right below the water table, and then 5 different depth intervals down to about 27 feet, where at the lowest levels, the samples were collected in a lower permeability silty clay sand. The other 4 samples at each location were collected in more of a fine to medium sand. So using radial diagrams, we're going to look at 8 different PFAS constituents and how they varied throughout that cross-section that we just saw. So you can see there's 8 axes. I've strategically kind of put the sulfonates on the top axes. So all 3 axes on the top are sulfonates. And then the bottom axes, the 5 axes, are all carboxylates. And then also strategically, we put the long chain PFAS on the left side in terms of axes, and the short chain PFAS are all on the right side of the radial diagram. And that way we can very quickly, looking at any one sample, we can look at the radial diagram and compare long chain versus short chain concentrations, or we can compare sulfonates to carboxylates. So that's one thing to keep in mind is we can look at these kind of comparisons depending on how we structure the radial diagrams. So you can see there's all axes have the same range from 0.01 microgram per liter up to 10 microgram per liter. And that allows us to see, to really compare which compounds are high and low at any one location. And then you can see there's 2 data series. The first data series is looking at the actual sample results from a specific boring and depth interval. And then the second series is what I call a reference series. And that's the maximum concentration of each PFAS constituent measured at any of these samples during this pre-remediation event. So the reference series is going to be the same for all the radial diagrams. The well samples, the sample results obviously change from sample to sample. So what I do when I look at this is I actually take a look at the difference between the maximum and the sample results. So we can see PFOA at this particular sample we're looking at, which is the up gradient boring near where the PRB was installed, right below the water table. And you can see at that sample, PFOA is about half an order of magnitude less than the maximum measured anywhere in this area. And you can look at PFBS, it's also close to an order of magnitude below the maximum. All the other compounds are pretty close. PFHXS also about half an order of magnitude below. Everything else pretty much at the maximum at this shallow sample. So that's one thing about reading these is when you have log scale for the axes, each tick mark pair represents a 1 order of magnitude change in concentration. So you can say, well, PFBS, it's close to a full, between the maximum and the well sample, you've got close to a full pair of tick mark change. That's close to an order of magnitude change. So we're really measuring orders of magnitude when we look at these, especially at AFFF sites where concentrations are high. So when we plot these on a map, you can see at the most shallow sample, that's where we've got about the highest concentrations for most of these compounds. And you can see SB2A to the right of that, right below the water table, everything's much lower, orders of magnitude lower. Same with SB3A, except for PFOA, which is high there. But all the other compounds are 1 to 2 orders of magnitude less than the maximum at SB3A. So that's telling us, well, we've got to have a shallow source, maybe pretty close to SB1, or maybe even above the water table at SB1. So that's one thing to think about. If you're thinking about an adsorption barrier, my recommendation is don't put them in a source area, put them down gradient, make sure you're down gradient of sources. So you want to do depth-specific characterization like this, make sure you're putting a PRB down gradient of where the sources are. You get the fastest decline down gradient that way. Now at this demonstration, we intentionally put it where PFAS concentrations were the highest, which is why the PRB was put next to SB1. If I was doing this for regulatory purposes, I would go a little bit more down gradient, put it where PFAS concentrations are actually the lowest, because you get the best longevity that way. And in terms of symbols, so one thing we're doing is we're plotting non-detect symbols. You can also plot exceedance symbols. PFOA, PFAS, PFHXS all have MCLs, and every single sample has exceedances of those compounds. So I didn't plot the exceedance symbols here, but I am plotting non-detect just to show that almost every, all samples but one had detections of all these PFAS compounds. So one thing to think about, I wanted to show too, with PFOA, so PFOA is the left axis. And if you look at SB1 and you look at the samples going down with depth, you can see PFOA is actually increasing with depth until it's the highest at the bottom. And SB2, SB3 also have the highest PFOA concentrations at the bottom of the aquifer where it's lower permeability. And that's actually pretty similar to what I've seen at a few other sites. I'm not sure exactly why, but that's interesting. PFAS tends to be highest closer to the water table. That's some sites I've looked at. Maybe it's related to adsorption to the water table interface. I'm not sure, air-water interface. But PFOA is definitely highest at that lower depth. Maybe it got dragged down a long time ago. That's something you might want to keep an eye on at sites you're looking at. And another thing to show is SB1A, for example, we've got high concentrations of both the short and the long chain compounds. So one thing to think about with precursors is 6,2-FTS, which is typically present at AFFF impacted sites. That actually degrades to 3 short chain carboxylates, the PFHXA, PEA, and to a lesser extent, PFBA as well. So one thing to look at is stacked bars, and that actually helps us look at proportions of short chain carboxylates to long chain carboxylates to sulfonates at any one location or in any sample. We might want to look at short versus long chain to get an idea of if we're seeing a lot of fluorotelmer sulfonate-based carboxylates in groundwater, was it more of a modern AFFF product that was released? Was it a legacy product or a mixture of both? And then we look at sulfonates versus carboxylates to understand different AFFF products that might have been released as well. So one thing with these stack bar maps, I mentioned these tick marks. These actually show kind of the cumulative proportion of each of these chemicals relative to the total of all 8 of these chemicals. And with the tick marks, it really helps us to visually estimate. Like, for example, I can look at the red, that's PFAS. I can tell very quickly PFAS is 30% of the total here. And I can tell that all the blues, well, those are the carboxylates, and they represent about 60% of the total. I also color these. So the shorter chain compounds are the lighter blues, and we can see they represent about 25% of the total. The long chains, especially PFOA, they're the darker blues, and the sulfonates are different colors as well. And we can see at this sample, we've got sulfonates are mainly PFAS, and the carboxylates are kind of a mixture of short and long chain. And we can see about 40% of what we might expect from an ECF-based AFFF are in this sample. About 60% of these products are probably from an FT-based product. So this kind of stack bar helps us visually look at AFFF different product contributions. And when you can actually overlay these on a site map, we can actually learn a lot more about spatial trends with these. So look at SB1A near the top. That's where we've got a pretty good distribution of short and long chain carboxylates. And SB1B a little deeper, we've got some short chain carboxylates there, but not much. And then all the other samples, they're almost all the long chain carboxylates. We really don't see the short chain carboxylates proportionally in the rest of the samples. So that's something to note. And I'll talk a little bit about precursors in a minute about why we might see that. So looking at precursor ratios, we're looking at 8.2 and 6.2 FTS, which are pretty high at this site. 4.2 is low. And we can see below the water table at SB1A, we've got high 6.2 and 8.2 FTS. The 6.2 degrades to the short chain carboxylates. When we add the oxygen concentrations on as another layer of information, now we can see, well, that 6.2 FTS is probably degrading to the short chain carboxylate, somewhere upgrading of SB1A. But we don't have those precursors down further with depth, which is probably why we don't see the short chain carboxylates with depth. So just another way of looking at a lot of chemicals on just a couple maps to better understand what's happening. All right, let's go see how the barrier performs. So one thing, so we've got groundwater moving into the barrier. We've got MW3S, a down gradient well, 5 feet down gradient of the barrier. And overlaying the water table, we can see at the time the barrier was installed, the water table depth was about 5 feet below ground surface. Got a clay layer up here, but you can see the water table really varies seasonally. We've got rainy events, or high rain events each year, and the water table varies. When we add the PFBS samples on from downgrading of the barrier, we see spikes in the PFBS, so we've got the high water table. So that's telling us, okay, when the water table goes up, it's probably picking up it's probably desorbing short chain and long chain PFAS from what used to be above the water table and causing intermittent mass flux downgrading of the barrier. And that's going to cause longer time to flush out that PFAS downgrading of the barrier. So this is where that cross section we looked at, if we wanted to increase the mass flushing time, probably better to go down gradient where we don't have shallow sources. But if this was a demonstration, we want to kind of look at worst case, which is why it's cited where it is. And this whole thing about the water table fluctuations described really well in a paper by Craig Devine et al. So now let's look at the actual barrier itself and what the sulfonate and carboxylate concentrations look like over time. So this is I mentioned 12-foot wide barrier. I keep getting the width and the length mixed up, but it's 12 feet wide. It is 30 feet long. I'm just showing a simple plan view map here. And we can see the first well in the barrier. It's about 5 feet into the barrier. And you can see so the outer data series, the dotted line, that's pre-remediation concentrations. And the much smaller yellow data series, that's 3 months after the injection at the barrier well. And we can see PFAS, for example, has declined by 3.5 orders of magnitude. PFHXS about the same amount. PFBS by 2 orders of magnitude. We've got some non-detect symbols in there, which is good. That's helpful to show when we're looking at remediation data. So that's showing 3 months in, very effective. Everything dropped right down to really low levels and non-detect levels. So adding a second data series or third data series, now we're looking at 2 years after the injection. That's the blue data series. We've got small increases in concentration at pretty much most of these compounds, but just small. Like it's actually a stable increase. It increased about 6 months in, and it's been stable in time. So it's not breakthrough like you'd expect when everything comes through all at once. And this is probably because of that vertical heterogeneity I talked about earlier. The good thing is these are still really low concentrations. I'm showing exceedance symbols now. So PFAS does have a small, low-level exceedance at this first barrier well, but it's still a really low concentration. Then looking at the second well, this is 10 feet into the barrier. Everything is still really low after 2 years. That blue data series, a lot of non-detect symbols. You can see a really small detection of PFAS at that second well, but everything's low, everything's stable. So that's exactly what we want to see. Now going down gradient, this is where it gets a little bit more complicated. The yellow data series is 3 months after injection, and we can see everything drop pretty quickly, a little bit less so for PFAS, more so for the short chain compounds. And the blue data series, that's 2 years in. So PFAS has actually declined further over time. The short chain compounds have been kind of going up and down at this well because of this intermittent mass flux. And one thing I wanted to point out, if it was adsorption of, say, PFAS to the air-water interface and the water table goes up and down, we'd probably only see PFAS and the long chain compounds going up and down. But in these downgradient wells, we're actually seeing both short and long chain compounds uh, with these short-term peaks and then coming back down. And that's more indicative of the water table going up and desorbing something that used to be above the water table and bringing it back down. So we are seeing that. But when you go look at, say, 10 feet down gradient, the yellow data series, that's 3 months in, a small decrease in order of magnitude at most compounds. The blue data series is 2 years in, much bigger increases. So what that's showing is that, yes, things are decreasing down gradient, even with this water table fluctuation effect and the intermittent mass flux we're getting, but things are decreasing overall versus time. It's just pretty slow. And that's something to keep in mind is whether you're doing an adsorption barrier or putting in a pump and treat containment system. If you're putting that in the middle of a plume and you're expecting things to desorb down gradient, you can expect it to take a fair bit of time, even just because of slow desorption or back diffusion. So just be aware that the desorption and flushing down gradient of these remedies may be longer than you think. Okay, so now we're going to look at carboxylates. Remember, these are a little different because the shortest chain carboxylates, PFBA, PFPEA, they don't adsorb as strongly. PFBA especially breaks through pretty quickly. PFPEA, it comes down, but it's not as low as some of the others got. And then looking at 2 years in, we see full breakthrough at the first barrier well for PFBA and PFPEA. We can see PFNA, PFOA are still pretty low concentrations, low level detection and exceedance for PFOA, but it's still quite low and it's stable. It's not increasing over time. And now I'm just plotting them all here. So looking at the second well in the barrier, we've still got really low concentrations and on-detect samples for almost all the long chain carboxylates. You can see PFPEA is starting to break through in that second well. So it doesn't last long, the shortest chain compounds in these barriers, but it's also not regulated in most jurisdictions. So that's okay if it's going to break through. It's the long chain ones that are regulated that we're really concerned about with longevity. And you can see down gradient, same as the sulfonates, the PMW4S well, for example, carboxylates decreased a little bit after 3 months, but big orders of magnitude decreases at that well after 2 years. And that's just showing it is certainly declining by orders of magnitude. But if we want to reach MCLs at some point down gradient, we can expect it to take some time. This just shows based on preliminary modeling, we're calibrating adsorption isotherms with that reactive transport model I talked about. This is being updated with newer information on CAC concentrations, but we're going to see something similar in the end. You can see the adsorption increases preferentially with chain length for the carboxylates and the sulfonates. And this was something I found interesting. When I look at desorption, the dotted lines are modeling desorption effects at the two wells, 5 feet and 10 feet down gradient, assuming equilibrium desorption, nothing to do, no effects of the water table. And you can see I expected really quick flushing, desorption for this compound, and all the compounds are the same. But we're seeing much more gradual flushing, really because we're getting this intermittent mass flux increase. We had a model kinetic desorption to try and represent the gradual decline. But just keep in mind that if you're putting in a barrier at a site, make sure you're looking down gradient of where the barrier is going to go, and make sure you don't have shallow PFAS smear zone around the water table that might cause a slow flushing down gradient. Okay, so that's the looking at visualization techniques in this 2-year study. I'm going to now show really quickly, because we don't have a lot of time left, what model results tell us about different options for where we place these barriers and how many you might place at a site. So this, also you can see we've got a paper out on this study. I wanted to acknowledge, I've got a number of authors here that you can see. Hunter Anderson was particularly supportive on this study. For this, we took an Air Force Base source area and used the source characteristics to basically simulate try and evaluate whether an adsorption barrier would even be effective. At the one site we looked at, it had really high PFAS concentrations. So we wanted to see, is adsorption really even a viable technology? And short answer is yes, with some caveats, but I'll go through this here. So this is the source area looking at this in plan view. And back of the envelope calculation, below the water table, we've got about 270 gram per year PFOA leaving the source area. Now, Hunter Anderson had actually worked on this site with others, with wood consultants, and they did a really interesting lysimeter study looking at pore water concentrations in the vadose zone above the water table and how they varied with depth. And they estimated how much mass was moving vertically down to the water table from the vadose zone. So you see the plan view on the right. The former burn pit is the orange zone there, the lysimeter locations. Just using radial diagrams again, outer data series of the maximum concentrations. You can see the sample results. We're showing exceedance symbols, non-detect symbols. And here we're showing only the compounds that had significant concentrations at this site. So plotting them on a map, you can see the one location to the right of the former burn pit that had by far the highest concentrations. And these are milligram per liter. That's not a typo. The pore water had 22 milligram per liter of 6,2 FTS. PFHXS was 10 milligram per liter. We don't actually have samples below the former burn pit because they had actually, I think, done remediation there for hydrocarbons quite a long time ago. So they did the lysimeter study outside of that area. So we've got really high concentrations, and this is 1 foot below the ground surface where there's a lot of clay material. Going down just 2 more feet, the next depth interval down, less clay material, much lower PFAS concentrations. PFAS declined by 2 orders of magnitude, by a factor of 100 at the next lowest interval down, but still pretty high concentrations. So taking all these data in this paper, they had actually done a mass discharge estimate of what's discharging. And for PFOA, they estimated 17 gram per year was discharging down to the water table. It's a low number because this is a semi-arid site. Infiltration rates were 2 to 5 centimeter per year, which is quite low, 1 to 2 inches per year. So it's a really small mass discharge of PFOA. Remember, we had 270 gram per year below the water table leaving the source area. So just quick mass balance, 17 gram per year from the vadose zone, 94% of the mass leaving that source area is actually coming from mass that's already below the water table. It's not coming from the vadose zone. So that's something you might want to look at it if you're evaluating what to do with a source area, how much money to spend, say, on a source area remediation versus something down gradient with an adsorption barrier. If you can estimate the mass discharge with a simple lysimeter study, that might really help you do some cost-benefit decision making. So we took the source characteristics, how much PFOA mass discharge really leaving the source area. We built a model, simpler hydrogeology than is actually present at the site. The whole purpose of this model was to look at representing the mass discharge and the concentrations of PFOA. The velocity is similar to what was at the site. The FOC is similar. And we wanted to see, can we actually remediate this kind of a plume with these really high concentrations using CAC? Or something like PlumeStop. And we looked at modeling 3 different alternatives. Alternative number 1 is looking only at one PRB. It's a downgradient adsorption barrier installed just upgrading of the property boundary. And this is right now we're looking at kind of a hypothetical plume. We didn't try to calibrate the plume to the actual plume at the site, which is a lot more complex. This is really representing the concentrations, the mass discharge, and the velocity. We've got about 400, actually the downgradient boundary is about 600 meters downgradient of the site. It's a fairly big Air Force base. So at this site, we looked at alternative 1 is 1 PRB at the boundary, and that's put it ahead of an expanding plume. It's not put in the middle of a plume where there's something downgraded. The second alternative is keeping the downgradient PRB and adding another PRB in the middle of the plume to try and cut off the high concentrations coming from the source area and actually see if that would increase the longevity of the downgraded PRB. And then finally, we looked at, well, if we could actually control the source, how long does it take to actually reach MCLs at the property boundary if that's all we did, just source control? So the results for this, we've actually got a video that's available online for download in the supporting information section of the paper. This first set, I didn't want to show a video on a webinar because they never work, but I'm going to show you what the results look like in the time series slides. So 5 years in, we see the plume is just reaching the downgradient barrier. 10 years, it's moving into the barrier slowly, pretty low concentrations, only up to 1 microgram per liter at the boundary. Now it's up at 40 years, we're up to 10 microgram per liter, just getting to the boundary. You start to see the PFOA plume moving slightly into the PRB, but it's still not moved much in because it's been pretty low concentration for a long time. Now concentrations are really getting high coming into the boundary and it's starting to move through more quickly. And that's the key thing. If you put a PRB like this in front of an expanding plume where concentrations are low initially, if it's an expanding plume, concentrations will increase. And they could increase by orders of magnitude. So make sure you take that into account when you're designing the carbon dose for a barrier. So we have breakthrough here at 66 years. And if we go through and look at the second alternative, now we've got a second PRB cutting that plume off. We see we've got separation now of the core of the plume after 5 years, 10, 20, 30, 40, 50. So 50 years, we still have a pretty big plume upgrading of the boundary. And we've got breakthrough of the first PRB at before 60 years. The downgraded PRB, we have breakthrough at 68 years. That's only 2 years longer than the alternative that had no mid-plume PRB. So what happened is, because there's so much distance between the first PRB and the second one, the effects of that first PRB didn't actually reach the second PRB until the PFOA plume had gone quite a long way into the PRB. So shorter sites, it might be more advantageous to do source control and put in a PRB down gradient. It might really increase the longevity of a barrier that way. But at large sites, it doesn't really make sense to put in multiple PRBs or even do source control. A down gradient PRB might be your best bang for the buck at larger sites. And this just shows with full source control, nothing leaving that source zone for 100 years, if that was the case. If you're going to accomplish that, because we've got high concentrations there, we're still well above the MCLs, orders of magnitude above the MCLs at the boundary after 100 years. So the most immediate impact to down gradient receptors is going to be accomplished by putting a barrier at the down gradient boundary. So just to wrap up, we're almost at the end here. So in terms of recommendations, what I've seen is these at AFFF sites, these are high concentration sites. We don't just have regulated PFAS. We've got precursors, we've got other PFAS. They all compete with our regulated PFAS for adsorption sites. We've got maybe DRO concentrations that can be high at some sites. So my suggestion, if you're going to look at an adsorption barrier, the further down gradient from a AFFF source area you can get, the better. The longer it's going to last, the less competition you have with the regulated PFAS of concern in the barrier. So that's one big suggestion. Go as far down gradient as you can. Don't expect things down gradient of a barrier or a pump and treat containment system to clean up quickly. It's probably going to take a while. Maybe focus on mass flux reduction as your interim goal, because that you can achieve pretty quickly. You can get some advantage, especially at smaller sites, by looking at source control with adsorption or other technologies. And you can add that to a downgraded PRB and really extend the longevity of a PRB in some cases. So for implementation, I suggest definitely visualization. You want to look at short chain versus long chain. Will precursors degrade to regulated PFAS? Modeling both PRB longevity and flushing time down gradient. Really set expectations with regulators and stakeholders on how long it's going to take to reach cleanup goals down gradient of wherever we're doing containment. And post-injection cores, I wouldn't do those. If you're going to do them at least a year after CAC injection, because it takes a while for that CAC to stabilize and attach. And definitely think about what you're going to do. Eventually, you might get breakthrough in these barriers. You've got to plan for reinjection, down gradient as a possibility, or maybe you're just waiting to see if new technologies get developed. So I think on that note, I'll finish up. A number of the papers I mentioned are at this link at our website. Or if you want more information on the visual PFAS for visualizing these radial diagrams and stack bars, you can go to the visualpfas.com page. Okay, so sorry, 5 minutes left, so I'll stop there. And I guess, Martin, we'll see if there are any questions.
Yeah, Grant, thanks so much. Some really good knowledge sharing there. Appreciate that. We do have some questions. So let's begin. We don't have much time. When you are fingerprinting sites, can you see differences between source contributions in a commingled plume?
I've had mixed success. I'd say some projects, let's say you've got two different sites where two completely different sources. Those I've actually seen successfully where one site tends to be more dominant in terms of the commingled plume signature. Other top projects I've seen where maybe similar products are used, or you don't really have that much of a different signature between sites, where it's harder to tell. The paper I talked about where we looked at the South Dakota Air Force Base, one thing we tried to look at was could we distinguish which AFFF products were used in the 12 or 13 different source areas at the site. And there were some clear differences, especially with the stack bar maps. Those were quite successful at showing different types of AFFF products being used in different source areas. So I'd say mixed success, but it all depends on your situation.
Perfect. Thanks for your question, Mauro Prado. Next question from Lara Lang. Hi, Grant. Thank you for your presentation. Learned a lot. One question. In your experience, how long do the barriers last?
Oh, that's a good question. So I've got a few papers published on this. There's a 2022 paper where we looked at 17 case studies, actual field implementations. They all were lasting for a long time, except for one site, an ethyl site with high organic matter in the groundwater, and that was causing inhibition of PFAS adsorption. Every other site, things were working well. The longest site that I'm aware of is actually Rick McGregor's site here in Canada. He's got, I think, the world's first successful in-situ remediation of PFAS using PlumeStop. And that site, he injected in 2016, so he is now 9 years in with no detections of PFAS after the injection in the source area. So that was really successful. There's another site that I know is 5 years in. In fact, Chuck Newell, I was on a paper recently with Chuck Newell and others at GSI, also looking at sites and longevity. So if anyone's interested, I can send you that paper as well. So I'd say when I model these, when I use the isotherms from groundwater samples that I've seen, if you design the barrier right, we should be able to design these to get at least 20 to 30 plus years of longevity, even with conservative assumptions. And that's what I suggest. Like, don't design something for 100 years longevity, because then you might be injecting more than you need to up front. It's more cost effective if you inject what you need to get 20 to 40 years of longevity, re-inject maybe 20 to 40 years down in the future. And if you look at net present value, that's much cheaper to do. So you don't want to over-design these. But most sites I've seen, you can design these for at least 30 plus years of longevity pretty easily. And Regenesis has a lot of experience with that as well. That's a question for them too.
Perfect. Okay, we've got a couple more questions from Richard Desrosiers. Several states are regulating shorter chains. So how does one understand when breakthrough might occur?
So it depends. So if PFBA is the one that doesn't absorb well to many sorbents I've seen. So if that's regulated, I think at least 2 or 3 states in the U.S. are regulating short chain. That's something where you would want to model that. One thing I do, so short chains are more effective by competitive absorption and actually chromatographic separation. PFBS absorbs longer than one would think. But PFBA, with a few sites I've seen, it hasn't absorbed well. I've seen sites where it has. It depends on the chemistry and what's in the groundwater. That's where if you're looking at this, I'd suggest talking to Regenesis or do a site-specific isotherm. Serum is doing these now as a commercial service. They'll take groundwater samples from sites, and they can tell you what the adsorption isotherm is for something like PFBA, PFBEA. But if you have a lot of sulfonates in the water, the PFBA may not absorb well. So if that's regulated, this might not be an effective technology. But you have to look at the site groundwater to really know.